May 18, 1945, Wilhelmshaven Naval Base, occupied Germany. The technical inspection team from Naval Group Command North moved slowly through the dockyard, where 3 American destroyers sat at anchor, their grey hulls bearing the scars of 2 years' Pacific combat. Korvettenkapitän Hans-Joachim Werner paused at the gangway of the lead vessel, a Fletcher-class destroyer designated DD-592. Her name, Hobson, was still visible beneath hastily applied German markings. These ships had not been captured in combat. Germany had surrendered 11 days earlier. These destroyers arrived as part of the Allied Naval Inspection Commission, allowing Soviet and German technical officers a supervised examination of Western naval equipment before the final partition of German assets. Werner's orders were straightforward: document American naval fire control capabilities for the technical archives. What he would discover in the next 6 hours would confirm suspicions that had haunted Kriegsmarine surface commanders since 1943. The Americans had not simply outbuilt Germany, they had fundamentally reimagined naval warfare through automation, and German gunners had been fighting at a speed disadvantage so severe it bordered on precognition. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Werner's assignment to this inspection reflected his unusual qualifications. He had served as gunnery officer aboard the destroyer Z-23 during the Channel Dash in February 1942, when Scharnhorst, Gneisenau, and Prinz Eugen had made their audacious daylight escape through the English Channel. He had witnessed British destroyer attacks, observed their fire control methods, and survived multiple engagements where split-second gunnery decisions meant the difference between hitting and being hit. More relevant to his current assignment, Werner had spent 6 months at the Naval Artillery School in Kiel, studying fire control theory and teaching young officers the complex manual calculations required to engage moving targets at sea. The German Navy had sophisticated fire control systems. The Bismarck-class battleships mounted some of the finest optical fire control equipment ever devised, with massive stereoscopic rangefinders providing accurate distance measurements out to 30,000 meters. German capital ships could engage targets with remarkable precision when conditions allowed careful setup and target tracking. But Werner understood the difference between excellent equipment operated manually and integrated automated systems. He had read intelligence reports about American surface actions in the Pacific, noting the disturbing frequency with which American destroyers engaged Japanese vessels at night, in poor visibility, achieving hit rates that suggested capabilities beyond what optical fire control alone could explain. The gangway watch, an American sailor with an MP armband, examined Werner's credentials and nodded him aboard. The destroyer was quiet, secured for inspection rather than combat operations, but Werner could sense the potential in every aspect of the design. At 2,500 tons full load displacement, the Fletcher-class was smaller than German destroyers of the Type 1936 A series, yet her 5.5-inch 38 caliber guns matched or exceeded the firepower of comparable Kriegsmarine vessels. More importantly, Werner noted the prominent director mounted atop the pilot house, a streamlined housing clearly designed for radar integration rather than purely optical fire control. Commander James Hawkins, the American liaison officer assigned to the inspection, met Werner on the main deck. Hawkins spoke passable German, having served as an assistant naval attaché in Berlin before the war. His orders, like Werner's, were straightforward: facilitate technical examination of specified systems while maintaining security classifications on certain advanced equipment. The Mark 37 gunfire control system, however, was not classified for this inspection. The war had ended. The Americans had no reason to conceal capabilities that had already determined naval battles across 2 oceans. Korvettenkapitän Werner? Hawkins extended his hand. Commander Hawkins, I understand you're interested in our fire control setup. Let me show you what we can, and I'll explain what I can't. Werner appreciated the directness. Commander, I have specific technical questions prepared by Naval Group Command. But first, I would simply like to observe the physical installation and understand the operational concept. In our system, Gunnery control is distributed between director, plotting room, and individual gun mounts with multiple manual steps at each stage. I understand the American approach differs significantly. Hawkins smiled slightly. That's one way to put it. Come with me. We'll start topside with the director, then go below to the plotting room where the actual computing happens. They climbed to the director platform, a position roughly 30 feet above the main deck that provided clear sight lines forward, aft, and to both beams. The Mark 37 director itself was an impressive piece of equipment, weighing 16 tons according to Hawkins's explanation, protected by half-inch armor plate against shell fragments. Werner noted the radar antenna mounted atop the director, a rectangular array approximately 4 feet long that Hawkins identified as the Mark 12 fire control radar. This radar, Hawkins explained, tapping the housing, gives us accurate range and bearing on surface targets out to about 30,000 yards in good conditions. Less in bad weather, but still enough to engage targets we can't visually acquire. The radar feeds data directly into the director's tracking system, which in turn feeds the computer below. Everything's integrated. Once we lock onto a target, the system generates a continuous firing solution as long as we maintain lock. Werner examined the director's interior through an open-access panel. The optical rangefinder was present, a 7-meter base rangefinder providing backup to the radar, but clearly secondary to the radar system. More interesting were the servo motors and gear trains, connecting the director's pointing mechanisms to electrical control systems. Unlike German directors, which required manual cranking to maintain target tracking, this system automated the heavy work of keeping massive guns pointed at a moving target while the ship itself pitched and rolled. How quickly can this director acquire and track a target? Werner asked, knowing this question went to the heart of the technological comparison he was mandated to document. Hawkins considered the question. From cold start, with the director pointing forward and a target appearing on the beam, we can be firing accurately within 5 to 6 seconds. That includes the time for the director to slew, the radar to lock, and the computer to generate a firing solution. If we're already tracking one target and shift to another nearby target, even faster. Maybe 3 seconds. Werner felt something cold settle in his stomach. 5 to 6 seconds from target acquisition to accurate fire. German fire control, using the same scenario, required manual rangefinder operation, manual plotting of target course and speed, manual calculation of firing solutions, and manual transmission of gun orders to each mount. Even with a well-trained crew, German destroyers needed 30 to 45 seconds to begin engaging an unexpected target with any accuracy. The Americans had a 7-to-1 speed advantage in reaction time, which in naval combat represented the difference between striking first and being struck first. And this is standard equipment? Werner asked. All American destroyers have this system? Every Fletcher-class destroyer, yes sir, 175 ships, also standard on our modern cruisers and battleships, though they mount multiple Mark 37 systems to control different gun batteries. The system was designed in the mid-30s and entered service in 1940. We've been refining it continuously since then, mainly through radar improvements and minor computer upgrades, but the basic concept hasn't changed. It's proven extremely reliable in combat. 175 destroyers. Werner did the mathematics mentally. Germany had commissioned 21 modern destroyers between 1936 and 1942 and had lost 17 of them by war's end. The Kriegsmarine's entire destroyer force, built over 6 years at enormous expense, numbered fewer ships than a single American destroyer class, and every one of those American ships carried fire control capabilities that exceeded anything Germany had mounted on surface vessels. Hawkins led Werner below decks to the plotting room, a cramped compartment deep within the ship's hull, where the Mark WWII fire control computer sat secured to the deck. Werner had expected a large apparatus, knowing computers required substantial mechanical components to perform ballistic calculations, but the physical size still impressed him. The computer weighed over 3,000 pounds, according to Hawkins, and consisted of hundreds of gears, cams, and servo motors arranged in a complex three-dimensional mechanism that physically represented the geometric and ballistic relationships between ship, target, and projectile flight path. "This is the brain of the system," Hawkins explained, gesturing to the computer. "The director feeds in target range, bearing, and angular rates, the stable element compensates for ship motion, and the computer generates gun orders continuously. Those orders go directly to servos on each gun mount, automatically pointing the guns. The gunners just load and fire when the firing circuits indicate proper alignment. The computer handles everything else, including fuse setting for anti-aircraft shells." Werner moved closer to the computer, examining the mechanical components through viewing ports in the protective housing. He recognized some concepts from German analog computers: the use of gears to represent angular relationships, the integration of rates to predict future positions, but the implementation exceeded anything he had seen. German fire control computers required manual input of target parameters and generated static solutions that gunners then applied manually. This machine generated continuous, automatically updated solutions, accounting for both target motion and the ship's own maneuvering. It was, in effect, a mechanical brain that removed human reaction time from the fire control loop. "The stable element," Werner said, pointing to a gyroscope-equipped unit mounted near the computer. "This compensates for ship motion in real time?" "Exactly. The gyros sense roll, pitch, and yaw. The stable element knows the ship's orientation relative to the actual horizon, even when we can't see the horizon, even at night in rough seas. It feeds correction signals to both the director and the computer, so the fire control solution remains accurate regardless of ship motion. German systems have something similar, I believe." "For anti-aircraft fire, yes," Werner admitted. "Our stabilisierte Leitstand, the stabilized director posts for heavy flak. But those are separate systems for anti-aircraft guns only. They are not integrated with surface fire control, and they are temperamental. Very heavy, very fragile, prone to mechanical failure. This equipment appears far more robust. It has to be. Destroyers take a beating, high speeds, violent maneuvering, heavy seas. Everything has to work when we need it. The whole system's been designed for reliability rather than theoretical perfection. Good enough accuracy, fast enough computation, robust enough to keep working in combat." That phrase, good enough accuracy, fast enough computation, crystallized something Werner had been considering since boarding the ship. German naval fire control pursued optimal accuracy through precise optical instruments, meticulous calculations, and highly trained specialists. The American approach accepted slightly reduced precision in exchange for speed, automation, and reliability that enabled average sailors to achieve combat effectiveness. German specialists struggled to match. It was the same philosophy evident in American tanks, aircraft, and logistics systems. Not the absolute best in any single metric, but optimized for practical combat effectiveness across all conditions. Hawkins demonstrated the system's operation in test mode, powering up the computer and director without actually pointing guns. Servo motors hummed as the computer ran through diagnostic cycles, mechanical components clicking with precise timing as gears meshed and cams rotated. Werner watched fascinated as range and bearing inputs from a mock tracking exercise generated continuous gun order outputs, the computer updating its solution multiple times per second without human intervention beyond the initial target designation. "How many men does this system require?" Werner asked. "In the director, we have 4. Director, officer, pointer, trainer, and rangefinder operator. In the plotting room, 3. Computer operator, radar operator, and a talker for communications. 7 men total control all 5 guns, and those guns fire independently once the system's locked on. For comparison, how many men does a German destroyer require for fire control?" Werner calculated mentally. "Director crew of 3, plotting room crew of 5, including the gunnery officer, and each gun mount requires a dedicated sight setter and trainer, so 10 additional men minimum, 18 total, and coordination between all positions requires constant voice communication through speaking tubes or telephone, manual at every step. Right. And every manual step adds time and introduces potential errors. This system removes most manual steps. Once we designate a target, the computer does the work. The only significant human input during engagement is the decision to fire. Everything else is automatic. Werner examined the fire control radar console, noting the circular display showing range and bearing information. The scope was dark now, secured for inspection, but he could visualize how it functioned in combat. The radar painted targets electronically, providing precise position data that fed directly into the computer's tracking algorithms. German naval radar existed, certainly. The Fumo 26 surface search radar on major warships provided detection capabilities, but German radar served primarily as an early warning system, alerting crews to target presence. The Americans had integrated radar into the actual fire control loop, using it to aim guns with precision in conditions where German optical systems became useless. The Battle off Samar, Werner said quietly. October 1944. Your escort carriers and destroyers engaged our Japanese allies' center force. The reports we received through Tokyo mentioned American destroyers engaging battleships with remarkable accuracy. Was this system responsible? Hawkins nodded slowly. I wasn't there personally, but yes. Destroyers like Johnston Hoel and Samuel B. Roberts used their Mark 37 systems to engage Yamato and other Japanese battleships. The Japanese had larger guns, thicker armor, more firepower, but our destroyers could maneuver violently while maintaining accurate fire. The automated fire control compensated for ship motion that would have made manual gunnery impossible. Those tin cans scored hits on battleships while taking evasive action at flank speed in heavy seas. The system works. Werner had read the action reports provided by Japanese liaison officers, 3 American destroyers and 4 destroyer escorts, engaging 4 battleships, 6 heavy cruisers, 2 light cruisers, and 11 destroyers. The American ships were massively outgunned, hopelessly outmatched by any rational calculation. Yet they had fought for hours, scoring numerous hits, disrupting the Japanese formation, and ultimately forcing the Japanese to withdraw. It made no tactical sense until one understood that American fire control gave those small ships the ability to hit while maneuvering at flank speed through shell splashes and smoke, conditions that rendered traditional optical fire control nearly useless. The tactical implications, Werner said, choosing his words carefully, are significant. If American destroyers can generate accurate firing solutions within 5 seconds and maintain those solutions while maneuvering violently, then traditional destroyer tactics based on careful positioning and deliberate gunnery become obsolete. The side with faster, more automated fire control can engage first, shift targets faster, and maintain fire through conditions that blind optical systems. That's exactly right, Hawkins confirmed. Early war, we worried about Japanese destroyers. They had excellent torpedoes, good gunnery, skilled crews. But once our Mark 37 equipped destroyers engaged them at night using radar fire control, the balance shifted. We could see them before they could see us, shoot accurately when they were still acquiring targets, and hit them before they could effectively return fire. It wasn't about individual ship quality or crew bravery, it was about system capability. Werner understood the implication left unspoken. The Kriegsmarine had possessed brave crews and reasonably capable ships, but bravery and capability meant little when facing opponents who could shoot accurately 5 times faster. German destroyers engaging American vessels would be like boxers fighting with one hand tied behind their backs, always reacting, never initiating, always half a minute behind the tactical situation. They moved forward to examine one of the 5-inch gun mounts, where the physical manifestation of the automated fire control became visible. The gun itself was a simple, robust design. The 5-inch 38 caliber Mark 12 was not the world's most powerful destroyer gun. German destroyers mounted 5.9-inch weapons with greater shell weight and longer range, But the American gun's 15 rounds per minute firing rate, combined with automated fire control, meant it could put more rounds on target in the critical first minute of engagement than larger, manually controlled weapons. More impressive than the gun was its mount. The Mark 30 turret enclosed the weapon, protecting the crew from weather and shell fragments, while servo motors slaved to the fire control computer automatically trained and elevated the gun. The gunners inside needed only to load shells and powder, then wait for the firing indicator light to signal proper alignment. When that light illuminated, pulling the trigger sent a shell toward a target the gunners might never have seen, aimed by a computer that continuously updated the firing solution faster than any human calculator could work. Ammunition handling, Hawkins explained, pointing to the ready ammunition rings surrounding the mount, is semi-automatic. Shell and powder load separately, but the loading cycle is fast, and the crew doesn't need to manually set fuses except for special projectiles. For anti-aircraft work, fuses are set automatically in the hoists based on range data from the computer. The system's designed so average sailors can maintain high rates of fire without extensive specialized training. That phrase again? Average sailors. German naval gunnery required specialists trained for months in complex procedures. American naval gunnery required competent sailors following simplified procedures, while automation handled the complex mathematics. The American approach meant ships could be manned by conscripts given basic training and still achieve combat effectiveness that took German crews years to develop. It was industrialized warfare applied to human skill, replacing artisan craftsmanship with assembly line efficiency. Werner requested permission to examine the ammunition storage and handling systems. Hawkins led him below to the forward magazine, where hundreds of 5-inch shells rested in racks designed for rapid access. The shells were standardized, interchangeable between all 5 guns. The powder charges came in cylindrical brass cases that simplified handling and prevented the loose powder issues that had plagued German ships. Everything was designed for speed and simplicity. Nothing was over-engineered or unnecessarily complex. Ammunition capacity? Werner asked, noting the extensive ready ammunition stocks. 300 rounds per gun, 1,500 rounds total. In heavy action, we can sustain fire for about 20 minutes at maximum rate, longer if we pace our fire. Replenishment at sea is possible but rarely necessary. Most engagements don't last long enough to exhaust magazines. 300 rounds per gun. Werner compared that mentally to German destroyer ammunition loads of 150 to 180 rounds per gun. The Americans carried nearly double the ammunition load, enabling sustained action without husbanding shells. Combined with faster fire control and higher rates of fire, American destroyers could throw more steel at targets in the first 5 minutes of combat than German destroyers could fire in 20 minutes. The mathematics of naval combat, which German planners had assumed favoured tactical skill and careful gunnery, actually favoured whoever could put the most rounds downrange fastest with acceptable accuracy. As they climbed back to the main deck, Werner noticed other details that reinforced the impression of systematic American technological superiority. The electrical generation capacity exceeded German destroyer standards, necessary to power radar, fire control servos, and automated systems. The damage control arrangements emphasized redundancy and subdivision, with multiple backup systems for critical functions. The crew accommodations, while cramped by any standard, reflected attention to habitability that German designers had sacrificed for performance characteristics. Everything about the Fletcher-class design emphasized practical combat effectiveness. Not a single system pursued theoretical perfection at the cost of reliability or ease of operation. The ships were built to be mass-produced by average shipyard workers, operated by rapidly trained crews, and maintained under austere conditions far from major ports. They represented American industrial philosophy, applied to naval architecture, and that philosophy had produced 175 nearly identical ships in 3 years. Germany, with its emphasis on individual ship sophistication and complex systems, had managed 21 destroyers in 6 years, and lost most of them. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Werner's written report, submitted to Naval Group Command 3 days later, ran to 48 pages of technical detail, diagrams, and comparative analysis. The conclusions, however, reduced to several stark observations. American naval fire control technology exceeded German capabilities by roughly 5 years of development time. The integration of radar, automated computation, and servo-controlled gun laying created a system-level advantage that individual German technical achievements could not match. Most critically, American ships could engage targets and shift fire between targets at speeds that made traditional German destroyer tactics obsolete before the first shot was fired. The report included Werner's assessment of what Germany would have needed to match American capabilities. First, reliable compact radar sets capable of precision tracking. German radar technology could detect targets but lacked the resolution and reliability for automated fire control. Second, a complete redesign of fire control computers to generate continuous solutions rather than static calculations. This required mathematical approaches German designers had considered but rejected as too complex for practical implementation. Third, electrical servo mechanisms powerful enough to control gun mounts while precise enough for accurate pointing. German electrical technology could build such systems individually, but lacked the standardization and manufacturing capacity to equip entire fleets. Fourth, and perhaps most important, a fundamental philosophical shift in design approach. German naval architecture pursued optimal performance in each individual system, accepting complexity and maintenance requirements in exchange for maximum capability. American naval architecture pursued adequate performance across all systems, emphasizing simplicity, reliability, and ease of mass production. The American approach meant their ships worked consistently in combat conditions, while German ships achieved higher peak performance when everything functioned correctly, which in extended operations rarely happened. Werner included cost estimates in his analysis. A Fletcher-class destroyer cost approximately $6 million to build in American shipyards working at high production rates. The equivalent German Type 1936A destroyer cost nearly 12 million Reichsmarks, approximately $3 million at pre-war exchange rates, but required twice the construction time and utilized specialized components that constrained production. The Americans built faster and cheaper while incorporating more sophisticated technology. The economic efficiency implied industrial maturity that Germany, for all its technical brilliance, simply had not achieved. The report's final section addressed the question Naval Group Command had posed. What would German destroyers have faced if they had engaged American Fletcher-class destroyers in surface action? Werner's analysis was blunt. German destroyers would have detected American ships at similar ranges using optical methods or radar. But upon initiating engagement, American ships would have begun firing accurately within 5 to 6 seconds. German ships would have required 30 to 45 seconds to generate initial firing solutions. In the critical first minute of combat, American destroyers would have fired 75 rounds per ship before German destroyers fired 15 rounds per ship. More critically, American destroyers could maneuver violently while maintaining accurate fire through automated stabilization and continuous computer solutions. German destroyers required relatively steady courses during gunnery, sacrificing maneuverability for accuracy. In any sustained engagement, American destroyers could hit while evading, whereas German destroyers had to choose between shooting accurately or maneuvering defensively. The tactical situation would resemble aerial combat between aircraft with different turn rates. The more maneuverable aircraft dictates engagement terms, while the less maneuverable aircraft fights defensively until inevitable defeat. Werner concluded that German destroyers would have achieved unfavorable exchange rates against American destroyers of 4-to-1 or worse, meaning 4 German ships lost for every American ship sunk. Given that Germany possessed fewer than 24 modern destroyers at any point during the war, while America commissioned 175 Fletchers alone, plus numerous other destroyer classes, the strategic implications were obvious. Surface combat between Pacific American and German destroyers would have resulted in complete German defeat within months, not through superior American seamanship or courage, but through systematic technological advantages compounded by overwhelming numerical superiority. The report circulated through Naval Group Command, generating uncomfortable discussions among surviving senior officers. Many had suspected American technological capabilities exceeded German achievements, but few had grasped the magnitude of the gap. The Mark 37 fire control system represented not just an incremental advantage, but a fundamental change in how naval gunnery worked. It removed human reaction time from the engagement sequence, automated complex calculations, and functioned reliably in combat conditions that rendered traditional methods ineffective. What made the realization particularly bitter was the timing. The Americans had deployed this system in 1940, before the United States entered the war. While Germany fought Britain and Russia, spending enormous resources on tank production and artillery manufacture, the United States was quietly equipping its peacetime fleet with automated fire control systems that would prove decisive in naval combat. By the time Germany recognized the extent of American naval technology advantages in late 1943 or early 1944, the war's outcome was already determined. Technological gaps of this magnitude required years to close, and Germany no longer had years available. Senior technical officers at Naval Group Command recognized patterns in Werner's analysis that extended beyond fire control systems. American radar technology exceeded German achievements by similar margins. American sonar capabilities surpassed German underwater detection methods. American damage control practices, emphasized through extensive training and redundant systems, allowed ships to survive damage that would have sunk German vessels. In every measurable category of naval technology and operational practice, American forces had achieved systematic advantages that tactical skill could not overcome. The philosophical implications troubled German naval theorists more than the technical details. Germany had entered the war confident that superior engineering, rigorous training, and tactical innovation would compensate for numerical inferiority. The assumption proved catastrophically wrong. Modern industrial warfare rewarded whoever could mass-produce adequate technology reliably, operate it with average personnel, trained quickly, and maintain it under austere conditions. Germany excelled at producing sophisticated technology in limited quantities, operated by highly trained specialists, requiring extensive support infrastructure. That approach worked well in short wars of maneuver. It failed completely in sustained industrial conflicts against opponents with mature manufacturing capability. The fate of the Kriegsmarine's destroyer force illustrated these failures starkly. Of 21 modern destroyers commissioned between 1936 and 1942, 17 were lost to enemy action or accidents by May 1945. The losses resulted from multiple causes: British naval action, British air attack, Soviet submarines, mines, and operational accidents caused by mechanical failure or navigational error. But underlying every loss was Germany's inability to build enough ships to sustain the force, maintain existing ships adequately given material shortages, or develop technological countermeasures to Allied capabilities. German destroyers that survived to war's end did so largely by remaining in port, unable to operate due to fuel shortages, lacking crews after personnel were transferred to more critical assignments, or simply hiding from Allied air power that dominated the skies. When Germany surrendered, 3 modern destroyers remained in commission, and they were museum pieces documenting technological approaches that industrial warfare had rendered obsolete. The Americans, by contrast, commissioned 175 Fletchers and operated most of them continuously throughout the Pacific Campaign, from Guadalcanal in 1942 to Okinawa in 1945. The numerical comparison told the story: 3 versus 175. Werner's subsequent career illustrated how Germany processed uncomfortable technical truths in the war's aftermath. He was retained by the Allied Naval Technical Mission, serving as a liaison between Soviet and Western inspection teams examining German naval equipment. His expertise in fire control systems made him valuable for explaining German technology to Allied engineers and comparing German approaches to Allied methods. The work was simultaneously humbling and educational, revealing just how far German naval technology had fallen behind in critical areas. Soviet naval officers examining German fire control equipment expressed polite interest but little enthusiasm. They already possessed American fire control systems through Lend-Lease, had examined captured German equipment extensively, and recognized that American technology represented the future, while German technology represented sophisticated dead ends. British officers were more diplomatic, but reached similar conclusions. German optical fire control equipment was excellent. American automated fire control systems were revolutionary. By late 1945, Werner had access to American technical documentation on the Mark 37 system's development history. He learned that Hannibal Ford and William Newell, the designers of the Mark I computer, had begun work in the mid-1930s, based on earlier mechanical computers developed in the 1920s. The Americans had pursued automated fire control systematically for 20 years, refining mechanical computation methods, developing reliable servo systems, and integrating radar as it became available. The Mark 37 wasn't a sudden breakthrough, but the culmination of sustained development in a specific technical direction. Germany, meanwhile, had pursued multiple competing fire control approaches without standardization. Battleships used different systems than cruisers. Anti-aircraft fire control was separate from surface fire control. Individual ships sometimes mounted unique equipment based on specific requirements or shipyard capabilities. The lack of standardization meant improvements developed for one system couldn't easily transfer to others. It also complicated training, maintenance, and spare parts logistics. American standardization around the Mark 37 meant improvements benefited the entire destroyer fleet immediately, and trained personnel could transfer between ships without retraining. The post-war Allied Naval Technical Mission reports documented other examples of American systematic advantages. American shipyards had standardized destroyer construction around prefabricated modules that could be manufactured separately and assembled rapidly. German shipyards built each destroyer as a semi-custom project, with unique characteristics requiring specialized construction techniques. American welding technology and quality control exceeded German standards, producing stronger, lighter structures with less labor. German metallurgy was sophisticated, but German welding practices remained conservative, favoring heavier riveted construction that increased weight without improving strength. American naval doctrine emphasized defensive damage control as much as offensive capability. Fletcher-class destroyers incorporated extensive subdivision, redundant systems for critical functions, and automatic damage control equipment like CO2 flooding systems for fires. German destroyers emphasized offensive capability, accepting reduced defensive resilience to maximize gun power and speed. The doctrinal difference reflected broader philosophical approaches. Americans assumed ships would be damaged and designed for survivability. Germans assumed superiority would prevent damage and designed for maximum offensive power. The assumption proved disastrously wrong for Germany. Ships got damaged in combat. Ships with robust damage control survived and returned to service. Ships without adequate damage control sank from damage they might have survived with better practices. American destroyers like USS Laffey survived massive kamikaze attacks that would have sunk German destroyers within minutes. The difference wasn't hull strength or armor thickness. It was systematic attention to damage control, training, equipment, and doctrine that gave crews fighting chances against catastrophic damage. Werner's final contribution to the Allied Naval Technical Mission was a comparative analysis of German and American destroyer development philosophies from 1936 to 1945. The analysis tracked how each navy's design priorities influenced combat effectiveness, operational availability, and strategic impact. The conclusions validated what battlefield results had already demonstrated. American destroyers, while individually less sophisticated than German destroyers in some specific measures, achieved superior combat effectiveness through reliability, sustainability, and technological integration. German destroyers pursued maximum performance in controlled conditions. Sophisticated machinery delivered high speed when everything worked correctly. Powerful guns hit targets accurately when fire control calculations were performed carefully. Complex systems enabled impressive capabilities when maintained by skilled technicians with adequate spare parts and support infrastructure. But war rarely provided controlled conditions, careful setup time, or adequate support infrastructure. War provided chaos, confusion, equipment failure under stress, and inadequate maintenance under austere conditions. American destroyers accepted lower peak performance in exchange for consistent functionality across all conditions. Simpler machinery operated reliably with basic maintenance. Automated fire control hit targets adequately without careful manual calculation. Standardized systems enabled repairs using standard procedures and common spare parts. When war provided chaos and confusion, American ships continued operating effectively, while German ships struggled with mechanical failures, inadequate support, and doctrinal approaches optimized for conditions that rarely existed in actual combat. The strategic impact of these philosophical differences manifested in operational statistics. American destroyers achieved cumulative operational availability rates above 80% throughout the Pacific Campaign, meaning at any given time 4 out of 5 commissioned destroyers were available for operations. German destroyers never achieved sustained operational availability above 60% after 1942, and by 1944, only about 1/3 of surviving destroyers were operationally available at any time. The difference between 80% and 33% availability translated directly into combat power available for missions. High availability meant American destroyer flotillas could maintain continuous operations, sustain losses, integrate replacements, and remain effective fighting forces throughout multi-year campaigns. Low availability meant German destroyer flotillas struggled to assemble enough operational ships for major missions, couldn't sustain losses without losing combat effectiveness, and gradually withered into ineffectiveness as mechanical casualties exceeded new construction. Availability, more than individual ship quality, determined which navy could actually use its destroyers in combat. The Americans could. The Germans increasingly couldn't. Werner's analysis concluded that Germany's destroyer program represented strategic misdirection of scarce resources. The Type 1936 destroyers and their variants were individually impressive ships, but Germany built too few to achieve strategic impact, incorporated too much complexity for sustained operations, and pursued technical sophistication that translated poorly into combat effectiveness. If Germany had instead built simpler, more reliable destroyers in larger numbers using standardized components and automated systems, the Kriegsmarine might have achieved greater impact with fewer resources. But that conclusion itself revealed the deeper problem. Germany lacked the industrial maturity, standardization culture, and systems engineering expertise to build simple, reliable, mass-produced destroyers. German industry excelled at sophisticated craftsmanship and complex engineering. American industry excelled at mass production and systematic standardization. Each navy's destroyers reflected its nation's industrial capabilities. Germany couldn't have built Fletcher-class destroyers even with complete technical documentation because the ships required industrial capabilities and organizational practices Germany simply didn't possess. The Mark 37 fire control system exemplified this reality. The technical documentation Werner examined revealed that Ford Instrument Company manufactured the Mark I computers using precision manufacturing techniques developed for commercial instruments and industrial controls. The company employed hundreds of skilled machinists and engineers, working with standardized tolerances and quality control procedures, perfected over decades of commercial production. The servo motors came from General Electric, produced in quantities of thousands using automated winding equipment and testing procedures impossible to replicate in small batch production. German companies could have designed similar systems. German engineers possessed the technical knowledge to create automated fire control computers. But Germany lacked the industrial infrastructure to manufacture such systems in quantities needed to equip entire fleets at affordable costs with adequate reliability. German industry produced excellent prototypes and sophisticated limited production equipment. It could not produce thousands of identical, reliable, affordable units. That limitation constrained German military capability more decisively than any tactical or operational factor. By 1946, Werner had accepted appointment to the reconstituted German Navy Technical Service, working with Allied advisors to develop post-war German naval doctrine. The work involved studying American and British naval practices, identifying applicable lessons, and planning how a future German Navy might incorporate modern technology. The process required acknowledging how completely German naval thinking had failed during the war and accepting that German technological sophistication had proven strategically irrelevant against opponents with mature industrial capability. The lesson extended beyond naval matters. Germany's entire military-industrial approach had emphasized individual system excellence over systematic integration, sophisticated design over reliable production, and tactical quality over operational sustainability. That approach generated impressive demonstrations of technical capability and short-term tactical successes. It could not sustain industrial warfare against opponents who prioritized systematic capability, standardized production, and operational reliability. The American Mark 37 fire control system represented this philosophical divide perfectly. Not the best possible fire control system by any theoretical measure, but the most combat-effective system anyone actually fielded at scale. The final irony, which Werner noted in private correspondence with former Kriegsmarine colleagues, was that Germany had encountered American automated fire control systems in World War I. The USS Texas mounted the Ford Mark I Rangekeeper in 1916, 30 years before Werner examined the Mark 37 system aboard USS Hobson. German naval intelligence had documented the American system but dismissed it as unnecessarily complex compared to German manual fire control methods. 30 years later, dismissing American technological approaches as unnecessarily complex, Germany found itself fighting opponents whose supposedly unnecessary complexity had evolved into systematic advantages that decided naval campaigns. The destroyer examinations at Wilhelmshaven in May 1945 marked one of the final technical intelligence operations of World War II. Within months, the Allied powers divided German naval assets, scrapped most German warships, and dispersed German naval personnel. The three modern German destroyers that survived the war served briefly in Allied navies before being decommissioned and scrapped. The technical knowledge gained from examining German equipment contributed minimally to post-war naval development. The Americans and British already possessed superior technology and had little to learn from German practices. Werner's detailed reports on American fire control capabilities circulated within post-war German technical circles, contributing to understanding of how thoroughly Germany had lost the naval technology race. But the report's impact remained limited. The individuals who might have used such knowledge to reform German naval practices before the war had died, retired, or lacked resources to implement changes. The reports documented failures but couldn't retroactively prevent them. The Mark 37 fire control system remained in American service until the 1990s, eventually displaced by digital fire control computers that continued the evolution toward faster, more automated, more integrated systems. The basic philosophy, however, persisted. Remove human reaction time from fire, control loops, automate complex calculations, integrate all sensors into unified solutions, and prioritize reliability over theoretical perfection. The approach that gave American destroyers their 5-second advantage in 1944 remained the foundation for naval fire control into the digital age. For the German Navy, the lesson came too late to matter strategically. By the time Werner examined American fire control systems in May 1945, Germany had surrendered, the Kriegsmarine ceased to exist as an operational force, and German naval power had been effectively eliminated. The 5-second advantage that Mark 37 equipped destroyers possessed represented years of systematic American development that Germany could not match, could not counter, and could not survive. In the end, the story of German crews examining American destroyers and discovering 5-second fire control capabilities wasn't about capture or examination. It was about realization. The realization that industrial warfare rewarded systematic competence over individual excellence. the realization that technological sophistication meant nothing without the industrial capacity to mass produce and maintain it, the realization that opponents who appeared unsophisticated by German standards had actually developed mature, integrated systems that translated into overwhelming combat advantages. Werner's final report to Naval Group Command, submitted in June 1945, concluded with an observation that summarized everything his examination had revealed. The Americans did not defeat us through superior individual technology or better tactical doctrine. They defeated us by building adequate systems in overwhelming quantities, operating those systems reliably under all conditions, and sustaining operations through industrial capacity we could never match. Their fire control systems could engage targets in 5 seconds where ours required 45 seconds. That 30-second difference was merely one manifestation of systematic advantages that permeated every aspect of their naval capability. We lost not because their ships were better, but because their entire approach to naval warfare was better, and we lacked both the time and the industrial maturity to close the gap once we recognized it existed. The mathematics were irrefutable, the physics were unforgiving, the strategic implications were inescapable. 5 seconds versus 45 seconds, 175 ships versus 21, 80% availability versus 30% availability, systematic integration versus individual excellence, industrial maturity versus sophisticated craftsmanship. The numbers told the story clearly for those willing to read them. American naval power had rendered German naval thinking obsolete before the first shots were fired, and by the time German officers like Werner examined the evidence in May 1945, the lesson had already been written in the wreckage of 17 German destroyers lost to enemies they could neither match nor overcome. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.